Hello, everybody. Can you hear me?
Yes, I can.
Okay.
Yes, I can hear you. Yes, thank you.
Thank you for attending this webinar. My name is Ciprian Popa. I work at AllBeamNet, and I'm going to present a software solution developed under CI Engineer. Let me show you exactly what I'm going to present today. I don't want to exceed 1 hour, and there will be further webinars that will show more examples. So from what I read from the registration, not everybody is familiar with Glass and with CA Engineer. So I will show you a bit what are the challenges of starting to design glass structures, and what is the state of the art, and then I'll illustrate some practical examples of where glass structures come inside the buildings, and we'll discuss about the behavior of this material from structural point of view, but also chemical point of view and physical point of view. And then I will specifically talk about the technical aspects of this glass module and show you some practical examples done with C Engineer and this glass module. And then I will show you where you can find more, because this is quite a new realm, this glass design, and we want to share the knowledge with you, to have examples, to have step-by-step explanations, so that you will have the courage to start designing glass. You will see that glass is all around, and for this aspect I have prepared a movie for you. All right. What I wanted to show you that is the fact that glass is all around, and we structural engineers need to be able to design it. So usually this is a niche market where there are specialized offices, but then again, glass is more and more popular, and I think it's interesting to learn about it and then decide if we can step up in this industry. As you've seen, glass is used primarily in architecture for facades. This is the first thing everybody thinks when you say glass in buildings, but also for constructions. It can have roles as primary element or secondary elements, and in all malls, shopping area, you see they use for partitioning glass walls, staircase, as you've seen in the Google Apple Store, or beams and floors, which I will show in different cases throughout the world. Also, these windows and facades are made of glass and also have to be calculated from structural point of view and to prevent failures. And I will just go through some typical elements that you will find in any buildings. And this is actually the purpose of this webinar. I want to show that designing glass is also for engineers, and you might meet this demand in any building. So this is just shopping mall in Romania, and this is a glass balustrade positioned outside, and when there's an event, people just crowd and they sit here on this balustrade, and they put a lot of pressure on it. So somebody has to calculate this glass balustrade. Engineers are blocked. They know how to design the concrete columns, the steel parts, but they can get blocked with this kind of things, and the project can be sent later. Another example is for glass floors, which are used throughout museums more and more over. Glass stairs, which are very popular in the banks and also in the museums, and they are quite giving thrills to everybody. And glass roofs. So natural light is something that everybody wants to have. So if we design structures that are made of glass, so of course there is some steel in the connections, but you can see the sky, and it definitely creates a very nice environment. And this is just an example of a facade. This is something in Portugal. I've seen it at the airport, or the old version of Sea Engineer had something in Holland, something like this, a very big glass facade. As you've seen, this is the Apple store from New York on Fifth Avenue, which is it's actually the entrance. The store is underground, and this is made of, it's a glass cube that has ribs. So the columns are made of structural glass, the beams as well, and all the panels. And we don't resume to buildings. We also have passages in different shapes in combination with steel. And very impressive is this bridge in China, which I've shown in the model. It is a steel bridge, nobody can doubt it, but at the same time, people visit it just because of the glass decks that are positioned. And somebody has to be able to calculate it. It's similar to the British model from the London Bridge, where this is another reason why to visit them. So this was just an intro. Now we will go to glass, which is quite daring to say it's a structural material because of its lack of redundancy. Glass is an elastic material. So when we think of elastic material, we can compare it with steel or timber, where we have the possibility of yielding. So we can have plastic deformations and redistribution of tension. So in case we under-evaluate the loads, we can have distribution in plastic domains, and this way we can ensure some redundancy to the structure. While glass is perfectly elastic, but with brittle, unexpected failure. So this is something we have to take into consideration when designing glass. This is partially calibrated by the safety factors, but at the same time, when designing glass, there are a lot of failure scenarios. So actually, we have to take in consideration that some elements fail, and the other have to take the additional loads. And this is valid for even for very simple examples. So breaking one glass should not trigger the failure of the entire facade. There is a guidance for European structural glass, which is available for free on the internet, and I really recommend to get in depth with this glass part. It studies all the national design codes regarding glass, and also talks about what will be implemented in a future glass Eurocode. So it's very good if you study it. It's a free material. You just Google it and you'll find more. So glass as structural material, at the first glance, it's not a structural material due to the brittle behavior, and it will fail to stress concentrator. This means that we cannot design a linear element and see where we have the biggest bending moment or the biggest tension from axial force and bending moments, because that is not necessarily the point where it will break. Usually it breaks along the connections. So especially if we have point connections like spiders, that's the area that needs to be studied, because that is usually where the cracks appear or the failure comes from. So connection design is vital in glass. Also, glass is a bit unpredictable, and we will get to the chemical composition of it to understand why it behaves so. Here is a study made by Institute of Structural Engineers in UK, where they analyzed 740 test results on 6mm of annealed glass. And they got very different results. So from 40 megapascals or Newton per square millimeter to 120. So this leads to quite high safety factors because we need to choose where we need to be in the safe area, but at the same time have some economic margins. Another challenge when designing glass, and this is actually killing the hand calculation of glass, is the geometric nonlinear analysis. Glass is very strong, and we will see the properties of it. However, because of this, we can go with deflections that exceed the thickness. So when we start analyzing structures that with deflections higher than the thicknesses, then we have to go for the large deflection theory, which is quite complicated to do by hand. And this is one reason why we chose to develop under SIA, because SIA has the possibility of doing a third order analysis where it takes in consideration the geometrical nonlinear analysis. The problem is that if we go with linear analysis in some situation where we have big deflections, and this is a typical situation, especially in facades or big spans, we get higher tensions than reality. We can get double the tension. We can get to 49 newtons per square millimeters instead of 20. So if we perform a large deflection theory, we get larger deflections, but at the same time the stress are closer to the real stresses. So simplified is a bit over safe. What glass is made of? Well, mostly is made of silica, around 70%, and some other chemical components. The problem is that it does not build a crystal network. So if we don't have a crystal network, it's no stability. So this is where the unpredictability in the behavior of glass comes from. The fact that the structure is irregular, it doesn't have even a fixed melting point. So this is actually why it's so transparent, because the molecules are far away and it allows light to pass through. And in some situation, if we get a very good positioning of the molecules, we get strong glass. If they are randomly positioned and they have big distances in between the molecules, they will have a lower capacity. To produce glass, it's just going with those raw materials presented before in a melting furnace at 1600 degrees. And then there's some cooling happening. So it's a lowering of temperature, but not a very strict lower. And then an annealing process, they go through a float bath and enter an annealing process is where glass gets cooled and it's poured inside the form, and then it's cut and delivered as panes up to 6 meters long. Another aspect of the glass is the finishing and conditioning, which influences the capacity very much. So the finishing and conditioning has to be done in the factory. So actually when we are producing glass that needs to be delivered in buildings, they have to have the openings already positioned. So we need a lot of precision when we design glass structures because the tolerances are very weak and we cannot start to drill afterwards to have openings or holes. This is due to the fact that glass has a thermal treatment that strengthens it, and this will bring some tensions in one of the surface. So it's like pretensioning the glass, and that tension gets released when we try to insert an opening. So this is why the production needs to be known, so the production process and what treatments are applied. And we will see that exactly when I evaluate the strength of the glass. I will change different parameters from production point of view, and we'll see how the resistance, the capacity of the element changes. There are many national rules and regulations, but mostly as they say, there are rules. So there are a lot of proposed dimensions and a lot of confirming rules, so that the calculation of the glass can be avoided. And this happens a lot in Germany, for instance. For glass balustrades, there's actually a table, and according to geometry, if you respect the maximum length, the maximum height, and some load conditions, you can go through a table and select. If you don't want to respect, or the architect forces you to go outside of those norms, then you have the formulas to calculate. But as Germany, there's Austrian code, in Czech Republic, Dutch, British, French, and the Joint Research Center with these publications wants to create a single code, just like Eurocode, and it already released some pre-European norms, which is this pre-Euro norm 16,612 and this one. They are mostly similar. They have different, they add some rules, but mostly they have the same formulas for calculating the capacity, and it will consist the basis of glass Eurocode due to the fact that they are calibrated to the load coefficients of the Eurocode. So they will ensure the same fiability or reliability of the design. So we know that there's 2% or 10% chance to get a failure in 50 years. From what I've studied, the Eurocode are under revisions, and there will be a release of new updated codes. The trend is to simplify things. This is the trend. But I understand that the glass Eurocode will not be with the just next release. Hopefully, the other release will also bring the glass Eurocode. But as you've seen in the intro, that doesn't stop engineers from designing glass all around. This is a classification I made that somehow mirrors the modules that we developed at Allbeam. We have the monolithic glass. So this is the case where there's a single layer of glass. It can be any type of glass, centric glass, heat strengthened, but it's only one layer of glass. So the distribution of forces is done on a single layer shell element, and we determine the capacity of the element, we determine the distribution of forces and displacement, and the software performs a unity check and shows me where are the critical areas where it would fail, and it will also give me an engineering report. The next module is the laminated glass with interlayer. And here, this is actually the glass that it's used in construction. Maybe some of you are not familiar with laminated glass. The easiest way to tell about it is to think of a windshield. So if you've seen in the movies, when a windshield fails, it will not break in big shards and injure people. Shards will be small and will stick to a foil. So laminated glass is a glass made through several layers of glass, and an interlayer, which is usually done of PVB, polyvinyl butyrol. So it's just a very thin foil, and everything is placed in an oven, and under high temperature and high pressure, everything is glued together. So the advantages is that we can get cracks in one of the layers and the others will survive. Another aspect is the load sharing, which is very different. So the code will give us some idea of how to calculate the transfer of the loads from one layer to another. It's not straightforward. It actually depends on the load duration. So according to that, the code has a simplified method in which we can calculate an equivalent effective thickness for stress and an effective thickness for deflections. So this is a second module which will include the monolithic glass. And then there's the insulated glass, which is vital for facades. And we know that by 2020, we need to design green buildings. So we need to reduce as much as possible the consumption of energy. And this is why double and in some countries triple insulated glass is becoming mandatory. In Denmark, it will become mandatory to use triple glass. So this is another area where challenges occur. what is the problem with insulated glass? At first glance, there are just more layers of glass with a dispacer in between. The challenge of designing such a glass system is the fact that it will have a gas inside of it. So it will go inside of, it will be designed in a factory, it will be produced in a factory at a certain altitude, at a certain temperature, and then sent to a site which will be maybe from a high-rise building in the mountains or in a different area. The gas inside is subjected to temperature variation, and this will lead to a volume increase or decrease. So this volume transformation will be translated in an isochore pressure. So this isochore pressure will act in different directions in winter against summer, and it will actually manifest as an extra pressure on the glass panes. So aside from the wind load or impact load or maintenance load for these glass panes, there will be this extra provision or this extra pressure from the gas inside in between the glass panes. And another aspect is the fact that the load sharing in between the layers is quite complex. So if I push, you see here heat, but we imagine this is a force. If I push on one of the glass layers, it will act on the others through the glass, through the gas inside and through the insulator, and it will have a transformation. So there will be some coefficient that distributes the loads to the other glass panels. So this is another challenge, how we calculate this transfer coefficient. So there will be pressure, isochore pressure, and we need to distribute all loads, the inside loads or outer loads. And this design code covers everything, and everything is implemented in the software according to the design code presented before. So I will go briefly through the problems each module treats. So we have the monolithic glass design. This is basically the design formula used in the code, in the pre-European norm. So there are quite a lot of factors if we are to compare with steel or with concrete. So this gamma have the same notations as in Eurocode, so there are safety coefficients. But then there are a lot of factors that take in consideration the load duration or the surface treatment. And this is only for annealed glass, but usually we want to use prestressed glass, so there can be thermally toughened or thermally strengthened glass, which is far stronger than annealed glass. It can be 3 times stronger. And how is this strength achieved? This is due to a process. When the glass is getting cooled, one of the faces of the glass gets cooled faster than the other. So it will generate some compression forces. And when the glass will get tension, first the tension will consume that compression, and after then it will tension the glass. So this is the idea of prestressed glass, and this is why there are more parameters that get inside the determination of this capacity. You'll see that there are different parameters we can choose when we talk about the factory, and this will give values to all these coefficients. Our formulas are also transparent inside the software, and we'll see that in the practical examples. The laminated glass module adds some extra functionality compared to the previous one. So it will determine the capacity of each glass ply or each glass pane, but at the same time, in order to have a correct distribution of forces, it will calculate automatically the effective thickness for deflection and for stresses. So it will have an editor or a converter. We will input here the exact layers of glass that we are going to use, and we will choose the family type of the interlayer. So the interlayer is actually this foil that goes in between these layers, and this will affect for long-term deflection. It will creep and it will affect the effective thickness. So in order to have a correct distribution according to the code, we will model the glass with effective thickness when we calculate stresses, effective thickness for bending, and effective thickness for deflection. When we check the deflection of the glass. So this will be performed automatically by the software. And then we get to the insulated glass design, and here we have two modules, and one is referring to the double insulated glass, which is quite typical, and the other is for three-layer glass, so triple insulated glass. The code has very different algorithm of calculating the distribution factors for this and isochore pressures, and we managed at Allbeam to code both. And also I'll show we calibrated on the code. So the examples from the design code presents same results. So again, in this time we can make a combination. So we'll actually model each glass layer, and each glass layer can be single layer glass or laminated glass. So this is why this module, insulated glass, will include the single layer glass and the laminated glass. So with this module we can calculate everything. There are some extra parameters we need to input regarding the geometry, and the rest will be taken from the analysis software. So although this looks like a separate software, you will see that everything stays within the CI engineer. And I have prepared a practical example now to see how we can design a glass balustrade. So glass balustrade, all the times they are using laminated glass to ensure safety. And we will perform a ULS check, SLS check, and we'll go also through a failure scenario, which is mandatory. When one of the glass span fails and the other, through the steel railing, have to take the extra load. And we can also check the steel rail. So I will switch now to CI Engineer. And here we have these three models. We can work on a unique model. We can have construction stage model, or we can have different models. I wanted to keep things clear, from theoretical point of view. So this is why I copied this simple structure 3 times. So these are some glass panels. This is 1.1 meters, 2 meter long. And the glass panels are modeled as shell elements, and they have a thickness calculated. And I'll show you how I got to this 13.8 thickness. This is the deflection model. And when we go for the tension model, we'll see that there's something else is 15.4 millimeter, which will be kept also for the post-failure model. So we go to the load case. Something simple. I just inputted here the self-weight, calculated automatically by the software, and a lateral push of 0.75 kilonewtons per meter that act on the steel railing. So this is actually a steel element, simulates the handrail, and it also has a structural load. So when this glass fails, this steel element needs to be strong enough in order to transfer the loads to ADHN panels. Now let's have a look on how things look inside the software. So after we model the geometry and place the loads, we can create combinations. There can be linear combinations and non-linear combinations. We need non-linear for the geometric analysis. So here, one thing I did in SIA was to activate the module called non-linearity and the module called geometrical non-linearity. And then the model is already calculated. And after you install the software, we'll get to that point, but you'll just have to install a software. It will create a new icon on your computer, which is called add-ons. And depending on the license that you have, you will see that module. So here are the modules presented. There's one missing today, the triple insulated glass, but it will appear in the final kit. And each module has 2D member data. through which we can add additional attributes and information in order to calculate the glass, and the check itself. The check only can be seen after the model has been calculated and we know the forces. So what I'm going to do now is go for 2D member data for laminated glass. I'll go here in this dotted points, and here we can select from the database different types of glass. If it's surface pre-stressed, I will leave a soda lime silicate glass. This is the most typical. These information usually are taken from the glass producer. So if we ask glass producer, he needs to give us all this information also regarding the process. The glass surface, if the glass is sandblasted or not, and if pre-stress has occurred, which kind of toughening it's done. And usually the glass is thermally toughened because, as I said, it gives a boost of up to 3 times the capacity of annealed glass. Then there will be the loads. Here we need to input the proportion of the loads, because depending on the proportion of the loads, the K-mode factor will be calculated. So when we input here the values, we calibrate the K modulus, and it will affect the final capacity. And then for the deflection, there are different provisions to calculate the serviceability limit, and we need to specify the element type, and also we can input the element height. Why you have to input it? Because when we model glass, in this module at least, we will go with shell elements. We can start with linear elements, but in the end we'll transform everything into shells. Why we do that? Because, as I stated before, we need to see what happens with the load concentrators. So with the stress concentrators, we need to see exactly how the connection occurs and where they are present, because those are the points where the structure would fail. And then there's the edges. This is a provision that actually reduces to 90% the capacity if we want to consider the fact that the edge has been treated. And most of the time, edge is treated, because otherwise people can get cuts from it. We have seamed or polished edges. And then we get to the laminated, and here we input the load. This is just for the code. We need to keep this 0. We neglect the first layer, and we input here the thickness of the glass. So it can have as many layers as we want. So when we click, it will start to add more layers. But we will stick to 2 layers of 10 millimeters. And we can also choose the family of the interlayer type. So this is according to the European code. And when we choose the foil, or actually the producer of the laminated glass has to tell us which foil he used, this will influence the effective thickness. So what we choose here will influence the final effective thickness. I'll say save, OK. And what I did so far was to establish some 2D member data that I can add to different elements. So I can have a very complex model and have different thicknesses of glass. In this situation, I will keep things simple. So I just select everything, and it will add this additional data. And now I will select these glass panes and go for laminated glass stress check, current, and I will do a refresh to see some results. So we have different results. So SIA will display graphical the results. Now we actually see the unity check, but we can check principal stresses. Because glass is a brittle material, all checks need to be using principal stresses. So sigma 1 and sigma 2 are the ones that are needed to be checked. So if we want to manually, we know the capacity and manually check, we'd go for sigma 1, sigma 2. And if we want to see the capacity, we go with this value, FEGD. And then I can go with unity check, because it will show me the ratio between the force and the capacity. So as long as I am under 1, I am safe. If I'm under 0.5, it's not that economical. So we see here the distribution, the influencing of the corners, and this is the unity check shown graphically. and we can send this to an engineering report, even as 3D PDF. And further, we want to see what is this 058. It's like a black box. We don't trust this. It's glass. We're afraid. We need to understand what does this value mean. So to get to that value, we have to make sure that in the output, we select detailed and we go with preview. And then we see here how the capacity is evaluated, the K modulus, which depends on the load. This is the information it gets from when I selected the glass, and for that you can import the glass. So I already shared with you through email with material. This is the database of the glass. I shared it with you, and if you want to add it to your new project, although I'll include it in the shared example, you can read it from here. So I promise I'll show you. This is how we read it. So when we define the new project, you just select other material and read it from this file from the database. In future version, it will be automatically included in SIA, but for now, this is the way it will work. So this will show me the capacity of the glass, and it will also show me transparent formulas on how we got here. It will also tell me what is the allowable deflection, and I can check on this secondary model the allowable deflection. I think it's 24 millimeters, and I can go with 3D displacement and check the displacement, and I see what are the values, and from the SLS combination. And this is a post-failure model where some of the glass has failed, so the middle pane is missing here. So we will also check what's happening here. So I will go to add-on and perform the check from service SLU, ultimate limit state actually. So because of this lacking of intermediate panel, we have some stress concentrators here in the corners. So this can be prone to failure. And again, if we hit preview, we'll see exactly what it used to determine the capacity and how it compares to the unity check. And we can also have a look on what happens with the railing. So the steel part is actually part of the C engineer. So if I go now to steel, I can also perform a detailed check of this bar to see how it behaves under the load combinations, SLU, and we will run. We see that this fails from overall unity check. If I were to perform only a section check, for it, maybe it will be okay. And also here, it's the same principle as my glass module. If we go to preview, we'll see exactly what formulas have been used. So this is a brief, but we can go for a more detailed report, and we'll see exactly all parameters, buckling lengths, and so on. So what are the forces it's subjected to, and so on. So stress and section check and stability check, and this is just because we are inside the CI environment. I will continue with the double glazing design. So this is another module I want to present to you. So it's a double glazing. It has some gas in between the glass panes, and I want to show it here. So here we have more loads. So more loads have been defined. CI is excellent at combining loads according to Eurocode based on load grouping, but all this will be explained in the movies I will share with you, which show from the beginning how we apply loads. So there are different loads here. There are the wind loads and the wind load pressure and suction. Impose concentrated load in case of impacts or even maintenance loads. So if we have a rail here, and this climatic load during summer and winter has been calculated by the software. So the way we work with insulated glass, we have to model the glass panes at exactly their distances. So actually here we have different thicknesses for the elements. As I said before, they can be built from single layer or laminated glass. And additional from what we've seen so far is the fact that we can add here parameters regarding the production. So I will go with member data. I'll extend this window. We can input here panel geometry parameters. As I said, the panel can have any shape, but the code calibrates for rectangles. So this is why we can input here the parameters. And here we have the effective thicknesses. So with the first laminated glass module, we calculate the effective thickness, and we know what is the value we need to use. Then there's the glass cavity and the second effective thickness. Usually the glass in insulated units don't have the same thickness. So let's see what the software offers when it comes to this double insulated glass unit. So it will display different values. We can have phi, which is a load transfer coefficient. So we can have a brief result. This may not look that fascinating from brief report, but if we go with detail, we'll understand better what to do with this coefficient. So the software will calculate according to the parameters like the factory, the altitude of production. We'll calculate the stiffness coefficients of each pane, and then it will determine for us these tables, which is the final result, exactly like in the examples from the European code. We see the loads, and then we see the isochore pressure that acts on different layers in case of summer or in case of winter. And all this, what you see in the preview, can be exported to the engineering report. So everything is clear why we chose those coefficients when we determined forces. So if I have a force acting on pane 1, I have to take that force, which can be wind pressure, multiply it with this coefficient, and this coefficient to apply it to the second pane. And the same goes for a force acting the other way around. Let's get back to the rest of the presentation. I will show some more daring projects that can be calculated with this project. This is a project which is under construction actually in United Kingdom. So they are building a glass bridge, or we can say a glass swimming pool, in between two buildings. So it's a quite complex shape, and it's quite complex to calculate it by hand. And it's a daring project, but it's under construction actually. You can find a lot on YouTube. So I took some information from the internet regarding the thickness of the elements and made a model in SIA. It's a shell model. As I described, we need to model glass with shell elements. And there's the hydrostatic pressure of the water. So we apply water pressure, but also we generated the wind using the 3D wind modulator, 3D wind modeler from SIA Engineer. And we performed a third order analysis with large deflections. So we see exactly the correct distribution of forces. If we resume only to linear analysis, then we have higher stresses than in reality. So glass, it is expensive, but still we need to limit a bit the cost. So we need to calculate, if it's possible, closer to the real behavior, of course going through the partial safety factor. So it's a non-linear analysis performed by SIA engine. SIA has a very fast FEM analysis engine. It's developed by FEM Consulting. I think it's shared with Drupal. They have the same solver. So it will bring a different solution from linear and non-linear analysis. Usually in non-linear geometric analysis, we have higher deflections but smaller stresses. And we can see here, have a look on the displacements. Maybe they look a bit strange. They are due to the wind that I have applied sideways. And it's like an envelope of the biggest deflections. And also we can see here the stress distribution in each finite element on the deformed shape. So again, this although it's a single layer shell, I use the effective thickness calculated with that converter that I presented before. So that converter offered me the solution to know what is the effective thickness, and then I can do the unity check. So aside from looking at the stresses and thinking of myself opening an Excel and determining the capacity, we can just use the functionality in the software to determine the capacity based on our additional input. So this is a table of forces that can be included in the engineering report, and now we are performing this stress check. So we see a unity check of 0.73, which translates in 73 usage of the glass, and we see at the bottom where we have the biggest deflection and the biggest tensions. And again, if we switch to detailed report, we'll know exactly. Here we have a lot of stories because there are multiple. There are 10 layers of glass used. In case one breaks, the other will take over. And this is how it's calculated. And this is a validation if the model is good for stress analysis or for deflection analysis. And usually we have to perform both. And also this is the allowable deflection determined by the software according to the norms. Another project that we already shown, but it was among the first we studied when we calibrated the software, was the glass cube. So this is quite a daring project. It has 10 meter almost, 975 meters length. It's a perfect cube, and it's made of these glass fins. So this was actually modeled in all plan by an architect for this application, not for the real project, and imported through IFC. And the main advantage is that we can see exactly the distribution of forces and the distribution of unity check. So we don't have to simplify things. We can go directly through the full approach. And for France, on Eiffel Tower, so they start adding glass even on older buildings, and this is in the Eiffel Tower, and this is the Eiffel Tower modeled in CA Engineer. This is actually one of the reasons we chose CA Engineer, because it's very easy to model very complex structures with unlimited number of bars, and we included here this glass addition. So we wanted to see exactly how the glass takes the deflections of this very big building. So we modeled everything, and we can watch the stress concentrators and the unity check to see exactly how this structure behaves. Okay, some of the advantage of this solution. We are coming to close to an end. It's for the moment, it's for the European market, but we can add any database to it, or even you as user can add any glass from any producer you find locally. It designs according to this code, which will become the Euro code, and it supports all type of glass, laminated, double, triple, and so on. It performs the checks, ULS, SLS, and these features are provided by the CA environment, so it can do a general stability analysis to determine the alpha critical and perform the geometric nonlinear analysis. And also we want to localize it as strongly as possible. So depending on your demand, there are SIA dealers worldwide that are willing to translate it into your local language and to provide database of glass specific for your local material. For now, the software is translated in Romanian, in English, and in Portuguese, the Brazilian Portuguese. It's a BIM-ready software because we can import from IFC, and we can export back we can export back the IFC with the glass itself. And I will organize a second webinar to show exactly how we can perform this. An architect will model it in Allplan and will import in SIA and calculate a spider facade. So I will provide examples. So please follow this website, structuralglass.org, as here I will prepare examples. So you will have something to start with. So some example of glass balustrade, glass decks. So you know also the order from engineering point of view. and some video tutorials. And this is why I'm actually postponing with 1 week the release of the installation kit and the trial license, because I want the tutorials to include everything, to include also the geometry part, because I've seen half of the people that subscribe to this webinar don't use SIA and they are not familiar with the software. So these videos will be complete. We'll show you how to open the project, how to model everything. So the team is still working on finalizing the models, but they will include video tutorial and the file itself and some sample engineering projects. So on the website there will be a section called the trial, for which we can download the installation kit, and it will simply add those buttons into your SIA software. And I will follow up with another webinar. I'll let you know in advance when it will be available, well, where I'll show you this BIM workflow. So how we can model the facade in all plan engineering, for instance, and then take it into SIA and calculate exactly what happens with the connections as well. So SIA allows to work with very complex geometries, and it has a beam alignment tool functionality which recognizes all elements, so we can easily convert them in between shell and linear elements. So in the end, we'll know exactly what's happening to a very complex facade and have unitary engineering reports. So as just some key facts, it's an integrated solution, so it's working under SIA Engineer. It's inheriting all its strong points, like 64-bit solution. It's a BIM environment, and it allows you to also design the steel and aluminum elements, even concrete elements if they interact with our facade. And they will show you very transparent checks. And I think this is very important when we discuss about glass, and you need to go to a checker or to an insurer to make sure that everything is according to a code and everything is transparent. So my idea is to make the software so that it's not a black box. It shows exactly as if somebody did the calculation on paper, but at the same time we model it with finite elements, so we know exactly what happens in any bit of the glass. For now we have it, the software will be ready, the kit, which will be available next week, will be available in English, Romanian and Portuguese. There will be 3 packages. Of course, when you download the package and you ask for trial, you'll have all the packages. And we started with single layer, so this is the first module. The second is laminated, multi-layer, and includes the single layer checks. And the final is for the cladders, the facade designers. They will need everything, so they'll have all the modules included in this. But also the prices are proportional. So if you just want to model some stairs or some balustrade, you don't need to jump to more complex module. So if you are interested also in that part, feel free to contact me via the email. And now I exceeded a bit the expected time, but I'm open for some questions. So
speaking.
Hello.
Will be interesting for us. We can see how it calculates the glass stair.
Sure.
The next webinar.
Okay. Also, I'm very open to challenges from your side. So if you have any proposals, we can make some models for you. So my idea is that to produce first some very good documentation, so you learn exactly, and then you decide to go with it. So I want to keep things as transparent as possible. So for glass stairs, that's a very good topic, and we can make exactly that spiral glass or any glass stairs.
And architects agree now, and it's for the next future to use some glass stairs. And for us engineers, it's better to have a software to calculate the stairs.
I perfectly agree. Thank you. Are there any other questions? You have my email, and based on your questions, I will simply organize more webinars and publish them on structuralglass.org.